Talk to any concrete professional and they'll tell you the number one rule of concrete is this: it's pretty much guaranteed to crack. But not all cracking is considered equal, and there's a way to reinforce concrete to minimize its negative impacts. Hey, I'm Grady, and this is Practical Engineering. Today, we're talking about prestressed concrete. This video is sponsored by Dashlane. Never forget a password again. More on that later. Despite its excellent qualities as a structural material, concrete has some weaknesses too. One that we've discussed in previous videos is that it has almost no strength against tension. Concrete can withstand a tremendous amount of compressive stress, but when you try to pull it apart, it gives up easily. Concrete's other weakness is that it's brittle. It doesn't have any give or stretch or ductility. Combine these two weaknesses and you get cracks. Concrete loves to crack. And if you're designing or building something made of concrete, understanding how much and where it's going to crack can be the difference between the success and failure of your structure. To understand how engineers design reinforced concrete structures, first we have to understand design criteria, or the goals of the structure. The obvious goal that we all understand is that it shouldn't fall down. When a car drives over a bridge and the bridge doesn't collapse, the structure is achieving its design criterion of ultimate strength. But in many cases in structural engineering, avoiding collapse actually isn't the limiting design criteria. The other important goal is to avoid deflection or movement under load. Most structural members deflect quite a bit before they actually fail, and this can be bad news. The first reason why is perception. People don't feel safe on a structure that flexes and bends. We want our bridges and buildings to feel sturdy and immovable. The other reason is that things attached to the structure, like plaster or glass, might break if it deflects too much. In the case of concrete, deflection has another impact: cracks. The reinforcement within concrete is usually made from steel, and steel is much more elastic than concrete. So in order to mobilize the strength of the steel, first it has to stretch out a little bit. But unlike steel, concrete is brittle. It doesn't stretch, it cracks. So that often means that concrete has to crack before the rebar can take up any of the tensile stress of the member. This demonstration is from a test in a previous video showing a conventionally reinforced concrete beam. Go back and check out that video if you haven't seen it yet. Notice how the beam is resisting the load on it even though it's cracked at the bottom. It's meeting design criteria number 1, it's holding the load, in this case 6 tons, without failing. But it's not meeting design criteria number 2, serviceability. It's deflecting too much, and the concrete is cracked. Those cracks not only look bad, but in an actual structure they could allow water and contaminants into contact with the reinforcement, eventually causing it to corrode, weaken, and even fail. One solution to this problem of deflection in concrete members is pre-stressing, or putting compressive stress into the structural member before it gets put into service. This is normally accomplished by tensioning the reinforcement within the concrete. This gives a member a compressive stress that will balance the tensile stress imposed in the member once it's put into service. A conventionally reinforced concrete member doesn't have any compression to start with, so it will deflect too much well before it's in any danger of not being strong enough to hold the load. So with conventional reinforcement, you don't even get to take full advantage of the structural strength of the member. When you pre-stress the reinforcement within concrete, you don't necessarily increase the strength, but you do reduce its deflection. This balances out the maximum load allowed under each of the structural design criteria, allowing you to take fuller advantage of the strength of each material. There are 2 main ways to pre-stress reinforcement within concrete, and of course I built a demo to show how this works. The first one is pre-tensioning, and yes, that's a little bit confusing. It's pre-stressed because the steel is stressed before the member's put into service, but pre-tensioned because the steel is stressed before the concrete cures. To make this work, I had to build a little frame to go around my concrete beam. This frame will hold the steel in tension while the concrete cures. I installed threaded rods through the mold and frame, and then tensioned these rods by tightening the nuts. I tried to use the pitch of the ringing to get them at around the same tension, and you can see how much my frame is flexing from the force in these steel rods. The other method for pre-stressing steel is post-tensioning. In post-tensioning, the steel is stressed after the concrete cures, but still before the member is put into service. In this beam, I cast in smooth plastic sleeves in the mold. The steel rod can slide easily within these sleeves. Once both molds were prepared, I filled them up with concrete. And I finally got a construction-grade concrete vibrator as well. This machine helps get all the air bubbles out of fresh concrete before it cures, a process called consolidation. After the concrete's had some time to cure, it's time to test the beams out. On the pre-tension beam, I can unscrew the nuts and take off this frame. Because the concrete hardened around the bolts, the steel rods are still under tension inside the beam. I put it under the hydraulic press for testing, and the results are easy to see. In a conventionally reinforced beam where the steel is simply cast into the concrete without any tension, cracks start forming at around 4 tons. In the pre-tension beam, the cracks didn't appear until double that force, at around 8 tons. The tension already in the steel is able to take up the force of the press without requiring the beam to flex. For the post-tension beam, I inserted the steel reinforcement after the concrete had cured. Then I tightened the bolts on the rods to pre-stress the steel. Under the hydraulic press, the results are nearly identical. The tension in the steel held the beam in compression for much longer than a conventionally reinforced member could. Of course, the cracks eventually appear, but it takes much more force before they do. That's because adding force to the beam isn't necessarily creating tension at the bottom, but simply reducing the compression that's already been introduced through the tension in the steel rods. It's important to point out that we didn't make these beams any stronger. Both the steel and concrete have the same strength they would without pre-stressing. But we did increase the serviceability of the member by reducing the amount of deflection under load. Of course, none of these examples actually failed because of the reinforcement, and that wasn't the point of this demo, but it's still fun to test everything to failure. Prestressed concrete is used in all kinds of structures, from bridges to buildings to silos and tanks. It's a great way to minimize cracking and take fuller advantage of the incredible strength of reinforced concrete. Thank you for watching, and let me know what you think. Thanks to Dashlane for sponsoring this video. I've been the victim of at least 10 major online data breaches in my life, including Facebook, LinkedIn, and Equifax. Obviously, all those passwords have been changed, but if I was reusing the same password for all my online accounts, any data breach could give people access to my bank accounts, health records, and everything in between. Dashlane simplifies online security and password management by seamlessly integrating into your browser and syncing between any kind of device automatically. And it's more than just a password manager. Dashlane warns you if stolen personal information is found in a data breach, can help you change passwords without going through a maze of web page settings, and has dark web monitoring and a VPN. I've been using Dashlane for a while now, and I really enjoy the peace of mind knowing my online accounts each have their own password that I don't have to try and remember on my own. Support this channel and visit dashlane.com/practicalengineering to sign up for free. Use promo code practicalengineering to get 10% off a 1-year premium subscription. Again, thank you for watching, and let me know what you think.